Hi, everyone. So today we're going to continue trying to understand the ideas from last lecture, but we're going to approach it in a more systematic way. So let me remind you what we did on Wednesday. We took two toruses, which look like this, and we used them to create a new surface as follows. So I cut a disk out of one, remove that, cut a disk out of the other, remove that, and then I can glue these two surfaces along the disk to get a new surface, which maybe we call the two-hole donut. Okay, and so this is a powerful idea which lets us get new surfaces out of ones that we've already seen before. And so let's give it a name. So given two surfaces, x1 and x2, I can obtain a new surface by cutting a disk out of each of the old surfaces. And then gluing them together along that boundary circle. Okay, exactly like in this picture. So along the circle that was created when I removed the disk from each of the surfaces. So in the picture, here's x1, here's x2, and this circle is now a boundary of x1, and this circle is now a boundary of x2, and then I glue them together along those blue circles. This operation is called the connected sum. Of x1 and x2. And it's denoted with a hash symbol. So if I write x1 hash x2, that means I've cut a circle out of each of them and then glued them along those circles that I cut out. Okay, so this gives us a way of creating new surfaces, and it's useful to know what this looks like, this operation, in terms of polytopes. So let me just recall the example from Wednesday. So if I have two toruses, and it's important to label their edges different colors because we're going to be gluing them together. So how do I cut a disk out of each of these surfaces? Well, the way to do it so that I'll be able to glue them together is to cut the disk out in such a way that the boundary of the disk intersects one of the vertices. In this case, I chose the upper right vertex. So now the torus with the disk removed looks like this. And here I'll do this one. And now I'm going to stretch these surfaces. And I'm going to basically pull apart that vertex. And so the boundary circle that was right here, I'm pulling it apart so it becomes now one edge of the polytope, and this boundary circle is going to become this edge, like that. And I need to keep my edge labelings. And so notice that what happened here involves some stretching. So the new surface I have is, I have to do some stretching here to get a new polytope. And I'm going to stretch even more. So the next thing I do is I'm going to glue these along the boundary circle, which means just gluing these edges together. And so if I stretch it even further, I get an octagon. Where that gray edge maybe was right here. And so so the labelings I have are as follows. Okay, and so I obtain this octagon with these labelings. This is a surface that we've studied a lot. Maybe let's call this F. Well, call this F. It's one we've looked at before, and so using this new notation and this new definition of connected sum, we see that F is related to a torus because it's the connected sum of two toruses. Although technically there was some stretching involved, and so really F is not exactly equal, but it's just topologically equivalent to the connected sum of two tori. And all that means is that up to some stretching, which happened here and here, this connected sum is the same surface as F. Okay, and so to answer the question, what does this look like in terms of polytopes, you can see what happens. I basically just choose a vertex. In this case, I chose this one, and I choose a vertex here, and I glue these two together at the vertex and then stretch it out. So if I had polygon with 4 sides here and 4 sides here, I get something with 8 sides, and I keep the edge labelings as before. And so I end up with a new polytope with more sides, well, the same number of sides as the sum of the two polytopes I started with. And that's how I get a new surface represented by a polytope. Okay. So, more generally, let me just write that down. So if x1 looks something, just some, let's see. So let's say I have x1 as some big polytope, and I'm not going to draw the whole thing. And if x2 is some other large polytope, it could have many, many sides. And there's some edge labelings. I don't know, just some random edge labelings. Oops. Got to choose new colors. Then, and I'm not drawing the whole polytope, right? It could extend further before it connects back up. So then what I do is I just choose 2 vertices. It's not actually going to matter which ones I choose. And I create a new polytope by stretching this vertex out, stretching this vertex and this vertex out to create an edge that I can glue these along. And so what I end up with is the connected sum looks like oops. And, all of this is, I'm really only concerned with topological equivalence here. So I'm going to allow myself to stretch things as much as I want. Oops. Okay, let's see. And then, but again, I have to keep the same edge labelings. And so I get this big new polytope whose edges basically are all the edges of the previous two. And so in general, this is how you do it. Okay, and so this is a really great tool because now we can make many, many surfaces by taking stuff that we already have and doing connected sums with them. So as an example, I could take the real projective plane, RP2, which remember looks like at least up to topological equivalence, it's just a loon with edges identified with a twist. And I could take the connected sum of that with itself, for instance. So another loon with those edge identifications. Okay, and so what do I do to get the new polytope? So this connected sum. So the new one's going to have 4 sides, and I'm just, again, I'm just choosing a vertex and stretching things out along that vertex and then gluing them along that. So in this case, it looks like that. Okay. Maybe I'll stretch it a little more. Really, there's some stretching involved, so these equals should be just equivalence, topological equivalence. And so what I get is, after some stretching, I get a square with these edge identifications. Now, I claim that this, if I do some further stretching, actually, is equivalent to something that we've seen before. So what I'm going to do now is represent this surface in a different way by doing some cutting and gluing. So if I cut along this diagonal, I get 2 pieces. So I can represent it as these 2 pieces, but I have to keep my edge identifications. And I have to remember that, really these 2 pink lines are glued together. So looks like that with all those identifications. And what I want to do now is represent this in a different way by gluing along a different edge. So maybe I'll glue along the edge with the red arrow. So to do that, I'm going to have to take this triangle and flip it over so that the arrows are pointing in the same direction. And so if I flip it over, the blue arrow side is going to go here. So let's see. So I have, this is where the red arrows are. And then the pink on the top part here, the pink is pointing away from the red, so it still is. And here the pink is pointing, again, away from the red, so it's pointing in this direction now. after I flipped this piece over. And then the blue arrow here, it's pointing towards the red, and here it's pointing away from the red. Which, yeah, away from the red, which is down. Okay, and then if I stretch things a little more, so I'll do a squiggle because it's just topological equivalence, you see that we get something familiar. The two blue edges are being glued with no twist, and the pink edges are being glued with a twist. And this is exactly the Klein bottle K. Okay, and so what have we shown? So we've shown that that I can construct the Klein bottle, at least up to some stretching. It's topologically equivalent to the connected sum of RP2 with RP2. Okay. So we didn't get something new that time, but it's cool to see this relationship here. Okay, so I think what I'd like to do now is share with you the main theorem of the course, actually, or kind of the final result that we're going to prove in this course, which says that actually all surfaces satisfying a few conditions can be built in this way from things we've already seen. So here's the theorem. All surfaces without boundary. So of course, given any surface, I can like poke holes in it or cut disks out of it and stuff, but that's going to create boundary points. But all surfaces without boundary and with finite volume, so not the plane or not the hyperbolic plane, so I mean, of course I can stretch a surface to get something new, but up to stretching, so they're all topologically equivalent. So I can stretch them to get one of the following. To basically connected sums of some basic building blocks. So I could take the torus, that's going to be one of my basic building blocks, and I could connected sum it with itself some number of times, because of course, given a surface, even if it was a connected sum, I can connected sum with it. I can connected sum it with some other surface. So I can do this as many times as I want. So are topologically equivalent to one of the following: a bunch of toruses connected sum with each other, or a bunch of RP2s connected sum with each other. Some number of times. And so basically I get an infinite number of surfaces by just connecting a torus with itself multiple times. I get another infinite set by connecting RP2s to themselves multiple times. And there's one I'm missing here, which is the most simple one that we've seen before, the sphere. Okay. And so what this theorem is saying is that any surface you can create by taking any polygon and identifying edges together is going to be up to some stretching equal to one of these three for some number of connected sums, right? Like there's some number of T's or there's some number of RP2s that gives you the surface that you started with. Okay, so this is the theorem. We're going to spend next week trying to prove it. But one thing to notice is that you can already build things that aren't obviously on our list. So this implies, for instance, you might ask, well, what happens if I take the torus T and connected sum it with RP2? Well, it must be something on this list, if the theorem is true. So this implies that T connected sum RP2 can be expressed as something on the list. By the way, we've already seen that K, the Klein bottle, is already on this list, right? Because we saw that K is topologically equivalent to connected sum of two RP2s. T, of course, is on the list because it's the connected sum of it with itself just one time. And so the question is, what is this? If I want to write it as a connected sum of T's or connected sum of RP2s, what is it? And a homework exercise for you all is to show that T connected sum RP2 is topologically equivalent, so I can express it via some cutting and gluings to the Klein bottle connected sum RP2. But the Klein bottle we already saw was the same as two connected sum copies of RP2. And so using the fact that this part is equal to that, I get that T connected sum RP2 is topologically equivalent to three RP2s connected to each other. So it falls into the second category here. Okay, so see if you can show that. You also might want to ask, well, what happens if I take the connected sum of the sphere with something I know? That's not obviously on the list. So show, for instance, that T connected sum with the sphere S2, that's topologically equivalent to just T. I haven't done anything. And actually show that for any surface X, if I take X connected sum with the sphere S2, I get something that's topologically equivalent to X. So I haven't really changed anything. There's two ways to do this. One would be using polygons, and the other would be just thinking about it and drawing pictures using this kind of picture. And you should see if you can prove it both ways. Okay, I think that's it. Thank you.